Describe and explain the following 4 trends across period 3. So we're in a little space station, seems to be a tad overgrown. Here's a representation of the sodium and magnesium atoms. Sodium has 3 shells, as does magnesium, and the electron arrangement is shown below. Now notice that magnesium is smaller because, well, sodium has plus 11 charge on the nucleus and magnesium has plus 12, and so the plus 12 charge is drawing those electrons in closer to make it smaller. Now I tried to do chlorine, but it was just too complicated. But chlorine has a plus 17 charge on the nucleus, and that would make it even smaller, and I'll go into more detail a bit later once we're finished with this silliness. If I make a sodium ion, then I'll knock off the valence electron, so now it's just 2,8 instead of 2,8,1. And the charge on this sodium ion is going to be positive. I've removed a negative. It's making it a positive. And that's going to be smaller. This only has 2 shells, whereas the sodium atom had 3 shells. And the same is true for magnesium. If I knock off the 2 valence electrons, magnesium's a metal, and metals hate electrons. So it loses 2 electrons, it's in group 2. Now the magnesium will have a charge of plus 2, and it's called the magnesium ion. And notice that that's also smaller, it's only got 2 shells. But the magnesium ion is smaller still even than the sodium ion, because magnesium has a more positive charge in the centre, attracting in the remaining electrons. You also have to say that the electrons are in the same shell when you're making this sort of comparison, and more about that later. So metal ions are smaller than their parent atoms. Is that a donut? That is a donut. Donuts. See if Dr. Atkionson wants one. Take that, buddy. There you go. Now, chlorine, well, that's a non-metal and it loves electrons. It's going to receive an electron, so I'll just grab this one off the floor here. So if chlorine grabs an extra electron, it will turn from 287 to 288. And it will now be negative. I've added a negative electron, all electrons are negative, and I've made the negative chloride ion. Now this negative ion is bigger than the parent atom because I've added an extra electron and it's caused extra repulsion in the electron cloud, and it's caused it to puff out, if you will. And yes, you can use the word puff out. So that extra electron causes repulsion in the electron cloud and it puffs out. So negative ions are bigger than their parent atoms, and positive ions are smaller because they've lost a shell. Alright, let's just go over here. Oh, Dr. Atkionson, he's cleaning the windows. Now, I happen to know that he's attached by a bubble, by covalent bonds to the glass. Very strong covalent bonds. Give that a good clean there, sir. Oh, I wonder what this button does. Ah, this is the button that turns covalent bonds into van der Waals bonds. Let me just hit that and see what happens to the bonding of the hemisphere to the glass. Oh dear. I've replaced it with weaker bonds. Dr. Atkionson now is floating off into space. Off towards the planet. So this is the part of the periodic table that we need to look at, period 3. And let me draw a little sketch of the atomic radii. And you can see as you cross the period, the atomic radii decreases. So what's the reason for that? Well, as you can see, I'm writing down the charge of the nucleus there. As you go across the period, the charge of the nucleus increases. And so that's going to pull the electrons in closer to the nucleus. Higher charge, higher attraction for the nucleus. So, once again, the radius decreases across the period for the atoms. And the increasing nuclear charge attracts the electrons in closer. The IB also wants you to say that the electrons are added to the same shell. That's the second point in this 2-point question. Moving on to the ionic radii, well, if you remember, that pattern wasn't quite so straightforward. So it seems obvious that the metals and silicon have smaller ions and atoms. The sodium atom loses 1 electron to make a smaller ion, which is now 2,8, it's lost a shell. Magnesium, well, that loses 2 valence electrons and makes a smaller ion still. That's also lost a shell compared to its parent atom. Aluminium loses 3, That's smaller still. And silicon, well, there's 2 ions for silicon. The positive one, where you've lost a shell, well, that's going to be smaller. And the negative ion, well, the negative ion has 4 extra electrons compared to the atom. And so those electrons are going to puff out, are going to repel in the shell and make it even bigger. So the negative ion for silicon is much bigger. Same for phosphorus, sulfur and chlorine. Adding electrons has puffed out the shell, caused more repulsion, increased the radii. Now they all had the electronic arrangement of 288, and the reason the negative ions get smaller is again because of increased nuclear charge. So looking at the first ionization energy, sodium plus 11 and argon plus 18 for nuclear charge. You only need to know the general trend for the SL, which is what this assessment statement's about. And so the general trend is that as you go across period 3, the ionization energy increases. And the general trend is because, well, the electron on the valence shell of sodium is so far away from the pull of the nucleus, it doesn't require much energy to remove it. And argon, the electron's so close to the pull of the nucleus, higher charge nucleus, that it requires a lot more energy to remove it. So that has a higher first ionization energy. So a higher energy you can think of as harder, and a lower energy as easier. So to reiterate, it's harder to pull the electron off of argon because the valence electron's closer to the pull of the nucleus. That's the IB preferred answer. You're also breaking a stable octet, but the IB doesn't normally give a point for that, so I wouldn't give that if I was you. And finally, for period 3, well, that number at the bottom seems to be increasing as you go across the period. So what is that? That is electronegativity. So as period 3 is crossed, the electronegativity increases. So why is that? Well, if I have an electron just randomly around, it's going to much rather go towards the chlorine compared to the sodium. Because when it gets to the chlorine, it can get closer to the nucleus or closer to the attraction of the nucleus. That's an even better answer.